Hello guys, so in this tutorial we will be dealing about the convolution and pooling layer of CNN and how to apply them using TensorFlow library inside Google Colab. So this is the third tutorial of our TensorFlow series. So in the past two videos you have seen how to apply basic neural network architecture using sequential and deep neural network. So using dense and flatten, what are the parameters required, what are the methods required to apply a basic model, what are the things required for your model.compile, model.fit, model.evaluate, model.predict, all this method and callback function, right? How to implement a callback class and how to call the class inside of our model.fit, right? So in today's lecture, we will be dealing about the basics of image data as we are working with fashion MNIST dataset, right? So we'll be dealing with that dataset as well, and we'll be dealing about convolution and pooling layer. Okay, so this was the previous example code that we were working. So first we were loading the fashion MNIST from fashion MNIST module, and as you know that the load dataset will give you two set of tuples, one training and one test set tuples, and each tuple contains two set of list. One contains the images, one contains the labels, and then we do the normalization of the pixel, and once that is done we use this callback approach in the second tutorial of TensorFlow series, and then we define the model, we print the summary, then we compile, we'll fit, and then we'll test the loss, right? So this is the uh, overall basic of the second class. You can do check. Now today we will be dealing about what is convolution neural network. So theories you have done, I think many videos or tutorials come across what is CNN or convolutional neural network. I'll just simply brief about this from this image. So let's say for any image data set you have this one as a image data set, that is 32 cross 32 image you have. Then you apply a convolutional neural network to it, or let's say a convolutional filter you applied. So what is happening in this filter inside, let's say you apply a 5 cross 5 filter and you apply 6 number of filters. So you can see a 6 number of image map got generated. So it is called as feature maps. So features being generated by applying convolutional filter on top of this image, and that's why it is called a feature map. Okay, and its pixel size will be definitely lesser than the actual input. So this pixel size got determined by the size of your convolutional filter. So here, as they have implemented 5 cross 5 convolutional neural network, I guess 5 cross 5 filters, so your 32 cross 32 image got reduced to 28 cross 28. Then max pool layer comes up 2 by 2, so your feature map got reduced again from 28 cross 28 to 14 cross 14. Then again there is I think 16 5 cross 5 convolutional neural network or convolutional layer they have applied. So your 6 feature of 14 cross 14 becomes 16 feature maps of 10 cross 10, and from this again a 2 by 2 max pool, that means 16 of 5 by 5 feature map, then dense layer. So this is how your convolutional neural network works. So if you see the pictorial representation here, these three lines we have already covered previously, right? Flatten layer, dense layer, and output layer, right? This is the additional thing that we need to apply today with the help of code for neural network use in convolutional cases. Okay, and how convolutional works in mathematical, this is the example. So this one is, let's say, your filter. Okay, let's say this one is your filter and let's say this one is your input. So the filter will get multiplied over this input image, the whole area, one by one. The default is slide by one. You can also slide by 2, 3, whatever you want. The default is slide by one, so that it can capture the most of the features basically, right? It should not skip anything, and once it captures, it will give you some output. Okay, so here is the small representation how it happens. So for the very first block, this one is the first block, right, as you can see in the image, and this one is the filter that is getting applied, and this sign is the convolutional sign. And once that is done, you will see the outputs are getting generated here. The outputs are nothing but the cumulative summation of this. Okay, so this is your overall convolutional neural network, and now we will see how to apply this one in code using TensorFlow. Okay, same thing, applications that we have like written here over. Two important module or methods we need to learn here. First one is convolution, second one is max pooling. So for implementing convolution in TensorFlow, this is the method conv2d, and in conv2d the required parameters are the filter, number of filters. Second one is the filter size, that means your kernel size. This one is default striding, so how you want your filter to stride from one pixel to another. Okay, next required thing is activation. This one is required, this activation. And for the very first layer, very first convolutional layer, that means for this convolutional layer, this C1, you need to mention the image size or the input size. Okay, so as we have discussed, four important parameters. First one is filter size, then first one is filter number, second one is kernel size, third one is activation, and final one is your input. And for the next number of convolutions, you don't have to mention this final input size. Okay, and in case of max pool, it is very simple, only the pole size you have to mention. Okay, whether it will be 2 by 2 or 1 by 1 or whatever, right? Okay, now let's come to the code. See, same sequential class we are going to introduce. So same sequential module basically, or function in the outer body we are implementing, because it will be under sequential. And this portion of code we have already seen, right? It will be as it is, only this convolution portion we have to add in code. So just pay close attention here. First method is convolution 2D, as we have just mentioned, conv 2D. So our convolution layer is going to going to apply here. 32 is the number of filter, 3 by 3 is your kernel size, activation function is ReLU, and input shape is 28 cross 28, and it is done. Then second comes max pooling again. 2 cross 2 is the pool size, and it is done. Again convolution, so conv2d is the method name, 32 is your filter size or filter number, 3 by 3 is your kernel size, your activation is ReLU, and you are done. Again, max pooling for this layer of convolution, 2 by 2 of pooling size, and it's done, right? So your whole model is, and then again you are doing a flattening, then a dense layer, then a dense layer for your final activation, and you are done with your model, machine learning model for CNN. That simple it is. So it's pretty much straightforward, step by step. Then again, what we are doing printing the summary. Once the summary is getting printed, then we are doing the compilation. For compilation, in the very first class we have mentioned, we require two things: one is optimizer, one is loss, and additionally we can mention the matrix along with losses, which is our default matrix. Once it is done, we need to fit will train the model on the training data. So this is the training level training images we are passing epochs. And in the second class we have also learned we can also include callbacks here. And once our training is done, model is loaded, then we do the evaluate or predict based on whatever data we have available. So we have test data available with us. So we are just taking the test loss by using this evaluate function, right? So I'm going to quickly run this cell to execute and see what is the output. So you can see this is the model it is generating, and this is the total number of parameters it has to train, approximately 1 lakh parameter, which is very less than the dense neural network case. Okay, so it has to train a very less number of parameters for a computer vision cases, and you will see that it will give much more accurate output as well. So I'll come back once this training is done or training is completed. So yeah, let this training goes by the time. Let's move on in the script. So in below you will see the exact explanation that I just mentioned or give to you in the code, what is happening. Same thing I have written here, you can go through it. Okay, what is the different parameter and values that we have used. So a quick recap, you need to remember for applying CNN, we require two additional things. One is convolution method and one is max pooling method. Okay. In max pooling, there is one required parameter, that is the strider. In convolution, there is four mandatory required parameters, that is number of filters, filter size, activation function, and for the first convolution, your input image shape or input image size. Okay, so once it is done, you can see the accuracy is close to 90% on the third epoch itself. So within 5 epochs you will get approximately 90 to 92% of accuracy. Okay, and one small case of overfitting, if you increase the number of epochs, you will definitely see a overfitted model. To reduce the model overfitting, there are bunch of methods available for any neural network method. So we'll be discussing all this once we'll be dealing with overfitting chapter, particularly later in the course. Okay, now next thing is your exploring of convolution. Okay, so we have already gone through what is convolution and how to apply convolution inside the neural network. So now if we have to understand this convolution method detailedly with a single image, right, how to do that. So for that, from Spacey we have included this ascent data set. Okay, so first we have to load this one. So if you called only this ascent method, right, from the SkyPy data set, it will get loaded. So once the data set is basically loaded, we can visualize the data. So you can see this one is the visualization of the data. So it's nothing but a stair. In the stair, two people, I guess, are going in upward direction. So this is the image. Okay, so on this image we will apply the method of convolution, and we will see like how convolution happens, or what convolution does to a image with different filters. Okay, so is our training done? Yeah, it's almost done. As you can see, now only the testing part is remaining. We have achieved approximately 92% of accuracy. So we'll just wait here for this model training to get completed, and then we can start. Yeah, so it is 92% on our training data set and 90% on our test data set, and we can start now understanding the convolution part as well. Okay, so yeah, moving forward towards this understanding of convolution. So let's just load this data set using ancient function. So once this function is loaded, our script is loaded, that means our image is loaded, and you can see the image, and all this using matplotlib's image show, basically this function. So you can also ignore this all this as well, right? If you comment out and then again do this, so you will see the image something with this x and y axis and the pixel values 512 512. So to make a better representation is we have included this lines basically. Hit enter. Okay, this is the image. So once this image is ready, we need to load that image into NumPy for numerical processing. So np.copy is the function. You have to remember this copy method, right? np.copy uses we will be using here to load the image, okay, as a NumPy array. So once it is loaded as NumPy array, we can do all sort of mathematical calculation. So we can also load the sizes of both x and y size, and we can print that as well in the next line. So once it is loaded, you can see the shape 512 512 in both the sizes, and you can also print the pixels of any value. Okay, so this is the 0th index in x size, that means your first row, 7th column, the pixel value is 82. Okay, so I think in this area looks like more white to me. That means if I go here in the line, let's say 30 and 7, it should give me much more whiter background. Okay, 30 is also, so if whole is 500, I think it is 100, it is 500. Let's increase it from 30 to 70, 90 approximately. So if it is becoming 100, yeah, so approximately 100 region, you can see 198. That means this portion of the image, right? This portion of the image is your, I mean, much more brighter and white compared to the other. Now let's just define this as the filter, basic filter we have. Okay, and just filters, let's keep it as nothing, and let's give a random weight of 1 so that everyone is equivalent. Okay, now what we are doing, we are running a loop here for x equals to 1 to the last to last element of x-axis, and y equals to again from the second element to last element of y-axis. And why we were doing this, because as you know, convolution we cannot apply it on this pixel, the border pixels, right? We cannot apply convolutions, okay, in the border pixels. We always required I mean, to apply convolution, some kind of padding in these places. Okay, okay, so for applying convolution, the method is pretty much simple. You take the corresponding image pixel, you apply with the corresponding filter, and you added those with the convolution. That means weighted sum, nothing but a cumulative sum kind of approach. So once that convolution value is done, you apply the convolution by weight. Right now we have taken with the weight equals to 1. Okay, so once the convolution value is computed, you just have to check, because it's a grayscale image. If your value is less than 0, we have to limit it towards 0. If the value is greater than 255, we have to limit it towards 255, because the grayscale has a scale between 0 to 255, right? 0 to 255. And once that is done, your image is transformed. That means filter is getting applied over your image. Okay, and then you can plot the image, the same image. As you can see, all the vertical railings are getting caught, because I didn't run this portion, right? So it pick up the by default default filter. So again, if I run this, you will see a different image this time. and now if you see, you will see a change image, right? So as you can see, it is defining all the borders. So without not the edges, all the borders of the objects it is defining. So you can clearly see, okay, there is a human being, there is another human being, these are the staircase is going upward direction, these are the column, these are the beams, you can see. So you can clearly get the whole structure. Okay, so by applying this filter, what you are getting, you are getting the border lines of the objects present in the images. Okay, now if you do a max spool on top of it, what you will get, you get the same picture in a distorted manner. That means that will represent approximation of what your convolution network captures. Okay, what this feature map captures, you will get exactly the same but with lesser pixel value. Okay, so this is the high concept. Okay, this is the concept behind this convolution and max pooling. So if I change the filter now, let's say I use a horizontal filter here. So this one is the horizontal filter. So if I use that one, and then again I do the calculation, you will see all the horizontal edges will get detected here. So let me just wait for completing of the cell, and you can see all the horizontal edges you can see here, right? All the horizontal edges you can see, and in the max pool you will see the same feature map but with lesser pixel value. So that means a distorted pixel value. So this one tells you the exact what features this image is storing with lesser amount of memory, right, as it has less pixel values. And the third one is the vertical filters. So if you activate the third one instead of second one, you will see all the vertical edges for the image. So let us just wait for this calculation to get over, and you can see all the vertical images, all the vertical edges getting replicated here very beautifully. And same thing you can also see here, right, after applying max pooling. So yeah, that's it for this convolution and max pool. You can also apply the same in any image. Let's say I have a tensorflow.png, and using OpenCV I load that. So this is actually the image looks like, and this is the grayscale representation. Then if I do apply the same convolution over final filter, that means a vertical filter, so you can see this one is the feature map representation of the image. That means it can clearly identify the vertical images of the actual image. So you can see here the vertical image, the vertical edges of the actual image are getting identified clearly here. So this is, and this is the distorted format of the same feature map in max pooling method. So that's it for today's video. So in this video we have learned the concept of convolution and feature map, and we have seen a detailed description how convolution works on top of an image, and how it extracts features from any image. If you like the video, please do consider a like, share and subscribe to the channel. We'll be coming with the fourth tutorial of TensorFlow series very soon. Thank you.